Hey, good afternoon, fellow statisticians, and today we'll be working out a few questions from Chapter 5, which is Discrete Probability Distributions from your Lint textbook. Okay? So the first question we'll be looking at is question number 64. Question number 64 is related to Poisson distribution. There's a women's fashion service, and they advertise same service delivery. And recently they've been having some problems, and the customer service director, Bud Owens over here, has completely redone the method of order handling, and their goal is to have fewer than 5 unfilled orders at the end of the day, at the end of 95% of the working days, right? And frequent checks are done, and after doing frequent checks, they reveal the distribution follows a Poisson distribution, and it has a mean of 2 orders. Okay, so the mean is 2 orders, and the goal is to have fewer than 5 unfulfilled orders. Okay, so if we try and write it down in the distribution, the mean mu is NP, and this is revealed to be 2. And the goal is to have less than 5 unfulfilled orders at the end of 95% of the working day. Okay, so the goal is to have P of X less than 5. Okay, this is what we are having right now, and the idea is like, what is this? Has the new process lived up to its internal goal? And cite evidence, right? By cite evidence, it means like show evidence using numbers. So how do you calculate this? So in some sense, the goal is given to you. So what is your, the distribution is given to you. So that makes it a lot easier that it's a Poisson distribution. So what is the Poisson distribution over here? It's the Poisson distribution can be thought of as probability of an event is going to be mu power x into e power minus mu divided by x factorial, right? So this is our probability. In certain videos, in certain textbooks, this mu is the same as lambda. At the end of the day, it represents the mean. Okay, so this is your Poisson distribution, and this is given as 2. But here, our goal is the probability of this x is less than 5 occurring, right? So this means what you're actually looking at is the probability of x is 0, plus probability of x is equal to 1, plus probability of x 2, plus probability of x is equal to 3, probability of x is equal to. So you need to calculate the probabilities of each and every one of them, and then add them all up. So this is the probability of x less than 5. Okay, all these 5 terms together. And once you find out the individual probabilities of these 5 terms together, you can find out the probability of x less than 5 happening. Okay, so we find this by going to Excel. So in Excel, you can find, here's the probability of x is equal to small x. And here's the mu, which is 2. And first, 0, 1, 2, 3, 4, 5. Okay, and so here, instead of doing this whole calculation, I am going to use an Excel function, which is the Poisson distribution function. So the Poisson distribution function is asked for x, and x is 0, the mean is 2, and it's asking whether it's accumulative. No, it's false. Okay, the probability of x being 0, as in there's 0 late deliveries, is 0.13%. The probability of there being 1 late unfilled order is 27%. And as you keep going, after 3 or 4, it starts going down a lot more. So these are the individual probabilities, and here we do not require this fifth. So because our goal over here is x is 0 plus 1 plus 2 plus 3 plus 4. Okay, so with these five values, the sum is going to be, okay, 0.94. So this is the probability x less than 5. Okay, so it's 0.9473. And what's our question? Our question is, the goal is to have fewer than 5 unfilled orders on hand at the end of 95%. So this means in 94.73% of the working days, you have only 2 unfilled orders. Okay, so there's like in some more than 5%. So that's very, very close to the goal, even if it's not quite the goal. Okay, so that's how we interpret. And the second part of your question is just draw a histogram. So once you actually have this table, the histogram is very easy, at least in Excel. So this is the probability, and insert histogram. Just going to go recommended charts. There's the histogram. Okay, so this is your probability. It's given to you of 0 times 0 unfilled orders, probability of 1 unfilled order, probability of 2 unfilled orders, 3, 4, and 5. But when it comes to histogram, you don't stop at 4. You try and go the whole distance. How we increase this here? So it's going to be 5, 6, 7, 8, 9, 10. Okay, so it gets small enough now. So I'm going to try and draw a histogram. Okay, there's the histogram. So after the 6 or 7, it's very, very rare that you get 7 unfilled orders in a day. It's 9. There's like a 9 and 10, and 8, 9, and 10 unfilled orders in a particular day is almost impossible. Like you'll never see it. This is your histogram. The next question which we'll be looking at is question number 74. Okay, so question 74 is it's Unilever. So it's a new body wash, okay, a ginger scented body wash. The research shows that 30% of the men like the new scent, and to further investigate, they randomly select 15 people, and you're being asked what's the probability that 6 or more people like the ginger scent. Okay. So this is a random selection of one event, and you're asking what's the probability out of these 15, the 6 people have, and your overall probability is given as 30%. Okay, so 30% is P. Okay, so this from all the even probability of success in some sense. All the signs, the question point towards a binomial distribution. So this is, you have random 15 people, and it's 15. And what do you want to know? What you want to know, what's the probability that 6 or more people like the ginger scent? Okay, so this is what you want to know. Probability that x is greater than or equal to 6. Okay, so this in terms of, again, similar to your previous question here, as soon as you have a greater than or equal to kind of thing, this is a cumulative distribution. So your binomial distribution, so what is the probability of x greater than or equal to 6? This is going to be the probability that is equal to 7, probability that is equal to 8, plus probability that x 9, plus 10, plus 11. And how many observations do you have? You have 15. It's all the way to probability of x is equal to 14, plus probability of x is equal to 15. Okay? So instead of doing this way, you have a lot of data points. You have like from 7 all the way to 15. This could also be written as the probability of x greater than or equal to 6 is 1 minus the probability that x is less than 6. Okay? And what's the probability that x is less than 6? This is going to be 1 minus the 1 minus the probability of x is 0 plus x is 1 is 2, x is 3, probability of x equal to 4 plus probability of x equal to 5. Okay, so this is one way to try and do this. So this way you need to calculate a lot fewer data points, right? You just have 1, 2, 3, 4, 5, 6 data points which you need to calculate as opposed to 9 data points over there, the greedy scenario. So using this, we are going to try and solve a problem. Okay. So the probability that here, again, probability that x greater than or equal to 6 is going to be probability that going to be 1 minus probability that x is less than 6. Okay, and so what do we do? Here we try and do something similar. Probability of x greater than x, so 0, 1, 2, 3, 4, 5. So we need to find out the values for these 5. And what is the probability over here? From a binomial distribution, you know that the probability of x occurring is ncx p power x 1 minus p whole power n minus x. Okay, so that is your binomial distribution. And you could make all these computations, but again, since I have Excel, I'm going to use their Excel functions. Okay, so this is their binomial distribution. What's the number of s? So in case, at any point of time, if you do not know what this function or how to use the function, at F1, it gives you all the details, the help menu, and you could go and try and learn about the function. Okay, so number of s is the required success in the trial, which is over here, x for x. Number of trials are 15. What's the probability of success? It's 30%. It's cumulative. Now we're trying. Okay, so the probability that you have 0 is going to be 0.0047. And you could find these out for everything else. Okay, so here when you try and think about it, the probability that 0 people like the ginger scent body wash is very low. The probability that 4 of them like the body wash, 5 of them like the body wash, you start getting some values here. In order to find out this okay, so this is the probability of x less than 6. Okay, so if you want to try and find out the probability that x is greater than or equal to 6, this is just going to be 1 minus this value, which is 0.278. Okay, so this is the probability that 6 people or greater like the ginger scent in the body wash. Okay, so another really fast way to actually do this is to obtain the same value is to try and do the cumulative distribution. But if you're not familiar with it, I would suggest not use it. So the probability of x less than or equal to 6, we found out by adding the previous 5 probabilities. You could also try and do the same thing as binomial. The number of successes is again 6, or here in this scenario is 5, because we're using 0, 1, 2, 3, 4, 5. Number of trials is 15, 30%, and cumulative, here you give true, and it's the same value. But remember, if I look into the function, I'm giving it 5 because the less than 6 is the next discrete number is 5 over here. So make sure you understand the function before you actually learn it. To begin with, I would suggest calculating things by hand until you get comfortable, and then start using Excel functions to speed up your process. Okay, so this is question number 74, and this is how you compute. You could try the same cumulative distribution function using the Poisson for this one as well. But I think it makes a lot more sense for understanding by creating these tables, especially in Excel, and where the calculation is a lot easier. Okay, so the next question which we are going to look at is question number 79. Question number 79 is the idea between Poisson versus binomial distribution in some sense, right? So what's the difference between Poisson and binomial distribution? Well, we didn't learn from a textbook that the Poisson distribution is typically used whenever you're thinking about counting or whenever there's some event related to time, right? The number of times something occurs in a specific interval, right? Or it could be distance or area or volume. Typical examples: how often can some flights be late, or how many flights per hour or per day which are late, right? Like how often vehicles are being stolen, how often does crime occur in a neighborhood, or whatever the thing is, anything which relates to time or some sort of continuum, you're typically using the Poisson distribution. But whenever the binomial distribution and the Poisson distribution are quite close in terms of their values, whenever n is great, okay, so the binomial, this is Poisson. So the binomial, the probability of x is ncx, e power x, 1 minus b power n minus x. And the mean is np. Okay, we have this as mu. The Poisson distribution, the probability of x is going to be the mu, the e power minus mu, x factorial. I think it's mu power x, if I remember. That's what the Poisson distribution, yeah, mu power x only. These are the probabilities for each of these distributions. And here as well, the mean mu is np. Okay, so in the binomial distribution, when n is infinity or very large, and the probability of success is close to zero, very small in general ways, and if their means are the same, then the binomial distribution is very close to the Poisson. Or the binomial distribution tends to go towards the Poisson distribution. So one way to actually try and do the check is by, here mu is the same as np, and so here the probability is going to be mu by n, and this, once you apply over here and try and compute and use what you call limits as n tends towards infinity, and if you solve for it, you could prove the binomial distribution tends towards the Poisson distribution. So this example over here, question number 79, we could try and figure out, we could try and compute them using both the binomial and using the Poisson and see how close the values are, and it doesn't really matter which distribution you use for this particular example. So here, what's the odds of a hole-in-one for a golfer? The probability of odds for a hole-in-one is very, very small. Okay, so question number 79. The probability of success is going to be 1 divided by 3709. That's the probability of success, which is hole-in-one. There are 155 golfers participating in the second round that day. Estimated the probability that 4 golfers would score a hole-in-one. Okay, so x is 4. Okay, so first let's do the binomial. So the binomial distribution is going to be The number of success, we're trying to find out that 4 golfers out of 155 can potentially score a goal in one. Number of trials is 155. Probability of success is this. Is it cumulative? No, it's false. It's a very, very small number. It's like extremely small. 10 power minus 7. And now we'll try and repeat the same using a Poisson. Why should they be close? Because the p is very, very small and n is fairly large, if not tending towards infinity. But the idea that p is very small should kind of make them fairly close. The Poisson distribution is going to be x, which is 4, and the mean, which is going to be 4 multiplied by 155, which is np. And so the cumulative, no, is false. Okay, so here also it's like very, very small. So the Poisson distribution is a little more accurate, but you get the idea that both are very, very small. So here, if you make the n even larger, it tends to go towards smaller, it becomes smaller and smaller. Okay, so this is the idea behind, but the binomial distribution is probably what you should use because n is not extremely large. So the binomial is more effective here. But you do see, even if you use the Poisson distribution, it's much, much smaller, but the binomial itself goes to like 0.000006. And this has like much more zeros, but that's the only difference. And I'm sure there could be other examples where they're a lot similar together, but I just wanted to point out the difference between binomial and Poisson for the same set of values. Okay, so that's it for chapter number 5, and I'll post another video on chapter number 6. See you all in the next video. Bye bye.